analyzing code corpora to improve the correctness and reliability of programs. Let me start by talking about the motivation behind this work. So dynamically typed languages such as JavaScript and Python have become popular in the recent times. And no matter what the language is used, bugs are expensive. And in fact, it has been estimated that developers spend a large amount of their time debugging, which amounts to millions of dollars. Now, bug detection is particularly challenging for dynamically typed languages because of the lack of statically declared types and also the dynamic nature of such languages. There has been some work to aid developers using these languages, mostly using program analysis techniques. But these techniques depend on predefined rules and sophisticated analysis, which can be expensive to execute. So then we ask the question, is there another way? Well, before I answer this, let me show you an example. So this is a bug that we obtained from a JavaScript library called phaser. The bug is very simple. To fix it, we simply need to change capital S in string to small s. Now, interestingly enough, 4 years later in the same library, the same bug gets repeated. So then we ask, what do we learn? Well, I would like to say that those who cannot remember the past are condemned to repeat it. Now, in this talk, I'll try to convince that analyzing large code corpora of dynamically typed languages provides opportunities to uncover repeated patterns. One such repeated pattern I just showed you in the previous slide. And such repeated pattern can be helpful in training learning-based approaches, and that are then useful to solve software engineering problems such as detecting inconsistencies, bugs in code, etc. So let me give you a brief overview of my dissertation. So you use a corpus of code that we either analyze using statically or dynamically, and then you use the output of this analysis to train learning-based models that are then useful, for example, for different tasks. We use it for bug finding. From the static direction, we have work such as we create many realistic bugs, or where our work include static analysis to extract natural language and source code to train machine learning models, which are helpful in finding bugs. From the dynamic perspective, we have works that where we find conflicts between JavaScript libraries by dynamic analysis, and also we find name value inconsistencies using by training machine learning models. And as a natural extension to our bug finding, we also use static analysis for input reduction. So in this talk, I will only go over the most recent of my two works. First part of this talk, I will go through SameSeed, and the second part, I will go over Nullin. So let me start with SameSeed. So which is a learning-based approach for creating realistic bugs. Now, it's a common wisdom that bugs are harmful. Then it begs the question, why seed them? Well, I can give you 3 examples that need large amount of bugs. So first 2 are to evaluate bug detectors and mutation testing approaches. And you also need large amount of bugs for training learning-based bug detectors. SameSeed is an approach for automatically creating such realistic bugs in a semantics-aware way. Now, the idea is very simple. Simply imitate bugs that occur in the wild, more specifically from top 100 GitHub projects. So let me give you a brief overview of how SameSeed works with an example. So SameSeed has 4 major steps. The first step is to have a bug fix that it can imitate, that I just explained earlier. So let's assume this is a bug fix that we obtained from GitHub, where the red part of the code is the buggy and the green part is the correct or fixed version of the code. The second step is to have a bug seeding pattern from this. So for obtaining the pattern, we simply flip the bug fix. That is, now the green part is in the top and the red part is at the bottom, and we abstract the identifiers and the literals. Now, the third step is to have a target program where we may seed the bug. So let's assume this is the target program, and in particular, this is the target location where we may mutate to seed the bug. Now, you might ask, how do we know that this is the target location? Well, if you notice the abstraction of the highlighted part on the code highlighted on the right matches exactly to the abstraction of the code that is highlighted on the left. And such kind of matches we call as syntactic match because of the abstraction matches. With SemSeed, our goal is to seed realistic bugs. And as a result, instead of purely relying on such syntactic matches, we also perform semantic match, and then we apply the pattern that gives us the seeded bug that we see at the bottom. So now let me explain how the semantic match and the pattern application works. Let me start with semantic match. So with semantic match, the goal is to check if two sequences of token are semantically similar. For this, we take inspirations from natural language processing, and we find cosine similarities of the token embeddings or the vector representations of identifiers and literals. And we use a heuristic that if the average cosine similarity is less than a certain threshold, we consider the token sequences to be semantic match. In this case, it happens to pass the heuristic. So we go to the next step, that is pattern application. So if you recall, this is the correct part of the bug fix that we are trying to imitate, and we want to mutate this token sequence, and the abstractions of both of these token sequence look like so. And this is the buggy part of the bug fix we are trying to imitate, whose abstractions look like so. And as a seeded bug, we want answer to the question mark tokens. Now, if you notice at the bug seeding pattern, from correct to buggy, these three tokens do not change. So we can simply follow the pattern and copy these three tokens. However, these two tokens changes. For the operator, we can simply copy. But what to do about this new literal that we need to seed the bug? When we encounter such situations where we need a new token for bug seeding, we call such token as unbound token. We use inspirations again from natural language processing to bind such unbound token. Let me show you how. So at this, this is the bug fix we are trying to imitate, and at this point of bug seeding, we want answer to this question mark token, which corresponds to Win32. And in particular, we use inspirations from NLP, as I said earlier. In particular, we perform analogy queries. So there are three queries that we perform. The first question we ask is which token is to process in the embedding space, as is Win32 is to process, which token is to Arch, as is Win32 is to platform, which token is to x64, as is Win32 is to Darwin. So these three questions gives us these three blue dots in the embedding space. And then we find the average of these blue dots, which gives us this red dot. And then we search around this red dot and select the closest token. So in this case, it happens to be x86, and we use it as the unbound token, and this concludes the bug seeding. So now that I have explained how bug seeding works, let me show you some results. We obtained 3,600 concrete bug fixes from GitHub repositories. And the specialty of these bug fixes is that they are simple single line changes, and then and the commit message contains keywords such as bug, fix, etc. From these bug fixes, we could extract 2,200 bug seeding patterns, and where we see that most of the bug seeding patterns contain at least one unbound token, at least 62% of them contain such. And traditional mutation approaches to seed bugs ignore these kind of patterns. The first question we ask is SemSeed able to reproduce real bugs using our technique? And for this, we see 10 bugs at each location where there is an unbound token. And then we compare that is our approach able to reproduce the real bugs. So we target around 53 bugs, and we find that using our technique, we can actually reproduce 47 of those 53 bugs. For comparison, a syntactic baseline could only seed 16 of those 53 bugs that we target. And the reason for that is that most of the cases, the syntactic baseline fails to guess the unbound token that is needed for seeding the bug. We also check if SemSeed generated bugs are useful, for example, training learning-based bug detectors. And for this, we use deep bugs, which need large number of correct and buggy examples for training. One of the reasons we choose deep bugs is that deep bugs has been adopted by the industry. The type of bugs that we use for training are wrong assignment bugs, where a developer writes O instead of writing I0. And then we train deep bugs using two separate data sets. The first is the default way of generating bugs. That is, in deep bugs, we call it artificial. The other is the SEMSID generated data set. And then we check deep bugs capability in finding real bugs. So these are the precision and recall of deep bugs on finding real bugs after being trained using these two data sets. And we find that SEMSID is indeed able to make deep bugs better, and deep bugs perform better when being trained using the SEMSID created dataset. So this concludes the first part of my talk. Now let me go over the second part, which is nullin, where we find name value inconsistencies from runtime value. So let me start by showing you two examples of name value inconsistencies. This part of code tries to split a data set into training and test and fails during execution. And the reason for the failure is the first line, where the training size, the variable name training size gets assigned the value 135.0, where it should be 135. And as a result, on the third line, the slice fails. It's not always so explicit. For example, in this code snippet, on the first line during execution, the variable name file gets assigned the value true or false, or the Boolean. Now, this is a misleading name because a more appropriate name would have been, variable name would have been file exist, for example. Now, although the top part of the code fails, the bottom code snippet doesn't, there's one thing that is common, and that is the name, the variable name, and the value that gets assigned to it are inconsistent. So in nullin, our goal is to find such name value inconsistencies. And while doing so, we face three challenges. The first challenge is to understand the meaning of names. And the second challenge we face is to understand the meaning of the values that gets assigned to these variable names. And finally, we also face the challenge of precisely pinpointing such unusual pairs of names and values. Now, let me give you a brief overview of how nullin works. So we start with a set of executable programs that we dynamically analyze to get name value pairs. And then we represent them as vectors and then use them to train neural models. For effective training of such models, we need examples of both names and values that are consistent and also inconsistent. So while during dynamic analysis, we get name value pairs that are consistent, the second step in our overview, we generate these negative examples. Then after training, we evaluate the model by querying, and this model then gives us many name value inconsistencies. So let me go over how we generate the negative examples, that is name value pairs that are inconsistent. One naive way that could be to randomly combine in name value pairs and then use it for training. Unfortunately, such naive approach can lead to many legitimate negative examples being created. And this will result in the generation of noisy training data and will lead the classifier to generate many false positives. So let me show you one such example of a naive approach, where, for example, this is a positive example where num is 3. And for creating a corresponding negative example, we search around, in our data set. These are the name value pairs let's say in our data set, and we randomly select one of the instance in the data set, and then we use the value from the selected instance, and then we create the negative example. As you can see that this such kind of examples where num gets assigned 32 can be created, and this is not a very good negative or inconsistent example because value 32 actually can be assigned to the variable name num. So instead of doing such naive approach, we perform a type-guided generation negative example where given a name, we select a type that is unusual for this name, and then also common across all observed values, and then we pick a random value for this type. So let me show you this with an example. So this is a positive example where the variable name years mm, has been assigned a list of years. And the first step that we do is that we find all types that years has been assigned to, and also the frequencies. As you can see, that years has been mostly assigned as list or ND array, and float and dict are unusual for being assigned to years. So what we do is that we use these unusual types and add it to all types that years has never been assigned to, and then we randomly select a type. In this case, this happens to be bool, and then use the value of the randomly selected type as the negative example. So this results in years is false. So this concludes the negative example generation part. And let me show you the architecture for a classifier. So in addition to just name and values, we also add certain properties such as the type of the value, the length of the value, and the shape of the value that we encode as vectors, and then we add all the information and pass it to a classifier, which outputs how likely a name and value pair is fits together. So let me show you some results. So our experimental setup consists of 1 million Jupyter notebooks that have been scratched from GitHub, of which we were able to instrument half of them. And during execution and filtering, we find 500,000 name value pairs that we use as the dataset. So this plot shows the effectiveness of our classifier in identifying a name value pair as inconsistent at different threshold. So the thresholds are the probabilities with which we can classify a name value pair to be inconsistent. And we find that we at threshold 0.4, our classifier has the best F1 score of 89%. We also check how useful is Nallin's prediction with a user study, where we ask developers to check if a particular name value pair is easy to understand and maintain. And in most of the cases, we see that Nallin's prediction matches with the developers' assessment. That is, we get a precision of 80% and a recall of 76%. Now let me show you the kinds of inconsistencies that Nallin finds. So we randomly take a sample 30 inconsistencies reported by Nallin, and then manually inspect them, of which we see that 21 are misleading names. So for example, one example would be for which there are 21 is where Nallin says it's inconsistent, where the variable name gets assigned the value 2.5. In code. Another example is incorrect value, of which we find 2 of them, where during execution, the variable name prob gets assigned the value corporate, which is of course wrong. And this actually, in fact, crashes the code in the later part. Nallin also, we found during a manual inspection that Nallin also produces some false positive. One such example is this, where the variable name dwar f gets assigned this value, the path, and where probably f means the file name. And we find 7 such cases out of the 30. So this concludes the second part of my talk. Now, to summarize, in the first part, I talked about SameSeed, where we use real bug fixes to mutate and obtain new bugs, which are realistic, and we find these new bugs to be useful for many things. For one of the application is training learning-based bug detectors. And in the second part of my talk, use executable programs that we dynamically analyze to obtain name value pairs, for which we generate negative examples using a type-guided approach and train neural models then we find are useful for pinpointing name value inconsistencies. This concludes my talk. Thank you very much for listening, and I would be happy to take questions.